The phosphorus cycle. Uh-oh. Here we go. Okay, so here's the goals. What we, the big focus for today, the phosphorus cycle as the other indicator for biogeochemical cycling planetary boundaries. So just a refresher, we have moved beyond the safe zone for both nitrogen and phosphorus loading in the broader environmental systems. So today we're gonna focus on phosphorus, and we're gonna understand how what the sort of natural, quote, natural phosphorus cycle without human intervention would look like, and what does phosphorus in our current system look like, and how does it move through the system. And then we're gonna have a special focus on how we could close the phosphorus cycle, as to use the terminology of one of the readings. So this is a little bit of a reminder. What do we have in our fertilizers? So big focus on nitrogen and phosphorus. And this is what we use in order to sustain our crop yields. So we talked about where the nitrogen comes from, or that's a separate topic of nitrogen cycling. And today we're going to talk about the phosphorus cycling. So this is a sort of elementary drawing of the natural phosphorus cycle. Most of it would be recycled within ecosystems. So you have rocks that contain phosphate, and this is the chemical formula for phosphate rock. And through weathering and erosion, again, this is very slow. Think about if you pour water on a rock, you're not going to watch it erode off into in real time, right? So we have a very slow weathering and erosion that's going to cause rocks to break down into different forms of phosphate that will then again be recycled in the system. And then some of it's actually going to end up in the biological system, where through the process of waste and decomposition, again, we talked about how animal waste can actually fertilize soil. So some of it's going to move into plants, some of it's going to go into animals, but then there's this recycling that's happening between plants and animals in real time. So most of the phosphorus moving through systems in a kind of human time frame is going to be recycled between animals and plants in, again, a natural cycle. And then some of this phosphate is going to end up moving into the oceans, and that phosphate is going to actually be moved into marine sediments, and over a very long time scale that can be moved back into rocks. And what's important to think about with this time scale is that in human time scale, right, so the 100 of years or tens of years, if you will, of us needing phosphate to put it back into the system, this that ends up as sediment, marine sediments, is lost. It's lost to the system for all practical purposes. So that's why we talk about this being kind of a one-way loop with, or one-way path with human modification. So again, let's remember, this is where we're at, right? So the planetary boundary was at 11 teragrams of phosphorus per year. Then where we are at, and that's global, right? So that's global phosphorus flow, and we're at these higher levels, right? So we're well beyond the safe zone and well beyond the zone of uncertainty for phosphorus. And then again, you can see also for nitrogen down here. So where does phosphorus come from? Phosphorus that we put into fertilizers comes from that phosphate rock that I talked about. And so that can be considered a non-renewable resource in the sense that there's a finite amount of phosphate rock on the planet that we can mine and turn into fertilizer. And once we have done that, because of the current system and how we're using it, we can consider that lost. But we'll talk about ways to close that loop later on in this talk here. So fertilizer use, remember this concept of the great acceleration, exponential growth in use beginning around 1950s. Notice prior to that, most of our phosphorus was coming from manure, right? So animal excrement that we would put onto fields in order to fertilize those fields. So primarily, horse and pig and cow manure can be used to fertilize fields. But what has happened in the mechanization and standardization of agriculture in the Green Revolution is we've turned agriculture from a system that should recycle itself into a high yield, high production system with large amounts of inputs. So rather than recycling manure in those systems, we've actually separated out a lot of those. Animals are now being grown on field, the name is now escaping me, in our CAFOs, feedlots, that's the word. And so they're not necessarily recycling that manure back into the environment. And then meanwhile, we're using this phosphate rock in order to fertilize our fields. So just like we talk about peak oil, or the moment when we will no longer be finding new reserves of oil, we have a similar concept in peak phosphorus, which is basically that after a certain year, and if you note on this graph, it's thought that we are quickly approaching that year, we will no longer be finding new global reserves, and in fact, production is going to begin to be significantly reduced after that year. If we can continue to consume, of course, all these models are if we continue to consume phosphate rock in the way that we have been for the last 50 to 60 years. So in the Childers et al. Article, they talk a bit about the inefficiency and waste in these altered phosphorus cycles. And the difference between these being, here we're seeing some actual numbers associated with these, this phosphorus that's moving, not in a loop, but actually in sort of a one-way path through the food system. And so if you can read all this through here to really dig through the details, but we have this phosphorus available for human use. We're putting it in agriculture. There's a lot of waste happening in the food supply. There's a lot of waste happening in our waste treatment and sewage treatment system. And so a vast majority of it is actually running off into the waterways and causing water quality problems or becoming sediment at the bottom of our marine ecosystems. So this is a more human intervention of the phosphate loop that you can see. So we're mining these wastes. We also have phosphates in our sewage. There's phosphates in fertilizer. And rather than reusing these in a more kind of sustainable farming system, we're allowing a good amount of them to flow off into our waterways and then become part of deep ocean sediments. And if we wait for plate tectonics to return those to phosphate rocks, humans will likely long have left the planet by then. So the geological timescale does not overlap with the timescale of us needing this phosphate rock. I like this. I'm not going to walk through all of it, but I have the slide here so that you can read through it in your own time. But it really just highlights the specific amounts of phosphate moving through the system and what some of the problems are associated with these phosphate flows. So here, this was in, I believe it was in your article. This is looking at the movement of where the phosphate rock is being produced and where it's ending up, right? So if you see reserves, right, and this is by continent, so pretty large scale, we're seeing these reserves of phosphorus, right, where the vast majority would be in the African continent. And then we're seeing here where the production is happening, so the refining and the making of fertilizer as like a higher value product, and then where is that consumption occurring? So you're seeing some inequalities in the use of this resource, and one might ask questions about who's benefiting, what people are benefiting from the production and use of this resource. And as we move into the future and this resource becomes more scarce, it is likely, along with any resource that becomes scarce, that some political tensions will arise. So First of all, this is just showing you regions of the earth where there are surpluses in phosphorus, right? Including fertilizer and manure application, and then areas where there are deficits, right? So this idea that there is a geographical inequality in the distribution of this phosphate resource, and as a resource so critical to the survival of humans in the sense of us needing to eat. It's similar to water in those essential life or goods for life that can cause some potentially catastrophic consequences and conflict down the road. So what can we do about this? Knowing that it's a finite resource, it's almost a little bit sad because hopefully you've looked at the reading and the potential for how we could close the human phosphorus cycle. And if you know those graphs that I showed, it was closed for centuries, thousands of years of human existence. And so it's not a terribly technologically challenging cycle to address. It's more about cost and I would say also a paradigm shift in how we think about our renewable and non-renewable resources. So here, for example, a potentially jarring example of growing corn with an experiment with urine. And you can see urine, which is high in these nitrogen and phosphorus wastes, would help feed your plants really nicely. Urine, in fact, particularly high in nitrogen, but illustrates the same point. And so one of the things that came up in the article is there, first of all, if we decrease the food waste, we're composting more, we treat our human waste in a way that we're actually returning that phosphorus and nitrogen to the system, which we have the technology available to be able to do this. Then we will actually see a huge reduction in the amount of phosphorus that's lost to the system. And we would not need so much phosphorus in the form of fertilizer. So this is just thinking about different ways that we could reduce our pressure on those phosphate rock resources. So reuse, right? Those are huge. Reusing food, reusing crop residues, human excreta, and manure. So all of those having really high ability to reduce the amount or recycle essentially the phosphorus that's already in our system. And all of this, the great part about it is all of this would apply to nitrogen as well, because all of these have high amounts of nitrogen and phosphorus in them. And then changing diets, we've talked a little bit about this, eating lower on the food chain would help with this. And then all of these possibilities from the efficiency standpoint. So we tend to over fertilize. We tend to not be, we were a very wasteful agricultural system. I'm sure you've all heard somewhat about, 40% of our food is actually wasted. And so we can create a lot more efficient use of resources in the food chain itself. And then here's just, some ideas in a table form. It's a bit more concrete, right? So things like fertilizer placement, what plants we're growing where, how we're rotating plants, working to improve soil long-term. All of those are ways that we're going to be able to reduce the loss of phosphorus into the surrounding ecosystem in a way that we cannot recover it. And then here are just some other ideas in terms of ways that we can recycle some of that phosphorus so that it's not lost into the system. All right, so phosphorus should be fairly straightforward. Again, quite similar to the concept of nitrogen, and hence we talk about them together as these biogeochemical cycles.